Okay, desktop finally went out of commission, so now I'm using my laptop. I wiped it. Let's see what happens, how it holds up. Back on Ubuntu too. Anyway, let's continue. New chapter, debugging. Debugging in Linux kernel, huh? Okay, so one factor that differentiates kernel development from user space development is the hardship associated with debugging. It is difficult relative to user space to debug the kernel. To complicate the matter, the stakes are much higher. A fault in the kernel can bring down the whole system. Success in debugging the kernel and ultimately success in kernel development as a whole is largely a function of your experience and understanding of the operating system. Sure, looks and charm help too, but to successfully debug kernel issues, you need to understand the kernel. This chapter looks at approaches to debugging the kernel. Getting started. Kernel debugging is often a long head scratching endeavor. Some bugs have perplexed the entire kernel development community for months. Fortunately for every one of these laborious issues, there are many simple bugs with an equally simple fix. With luck, all your bugs will remain simple and trivial. You will not know that, however, until you start investigating. For that, you first need a bug. It might sound silly, but you need a well defined and specific bug. It helps if it is reliably reproducible, at least for someone. But unfortunately, bugs are not always well behaved or well defined. A kernel version on which the bug exists. Knowing where the bug first appeared is even better. If you do not know that yet, if you do not yet know that, this chapter can teach you a trick for quickly determining it. Knowledge of the associated kernel code or luck. Debugging the kernel is tricky, and the more you understand the surrounding code, the better. Most of this chapter's techniques presume that you can reliably reproduce the bug. Your success in debugging relies on your ability to duplicate the problem. If you cannot, fixing the bug is limited to conceptualizing the problem and finding a flaw in the code. This does often happen, but chances of success are obviously much larger if you can reproduce the problem. So, bottom line is try to reproduce the problem. Life will be much easier. So, it might seem strange that there are bugs that someone cannot reproduce. In user space programs bugs are quite often a straightforward affair. For example, doing foo makes my application dump core. Bugs in the kernel are often much less clear. The interactions between the kernel, user space, and hardware are often delicate. Race conditions might rear their ugly heads only once in a million iterations of an algorithm. Poorly designed or even miscompiled code can result in acceptable performances on some systems, but terrible performances on others. It is common for some specific configuration on some random machine under some odd workload to trigger a bug otherwise unseen. The more information you have when tackling the bug, the better. Many times, if you can reliably reproduce the bug, you are more than halfway home. Bugs in the kernel. Bugs in the kernel can vary widely. They occur for a myriad reasons and manifest themselves in just as many forms. Bugs range from clearly incorrect code, for example, not storing the correct value in the proper place, to synchronization errors, not properly locking a shared variable, to incorrectly managing hardware, sending the wrong operations to the wrong control register. They manifest themselves as everything from poor performance to incorrect behavior to corrupted data to a deadlocked system. Often, it is a long chain of events that leads from the error in the code to the error witnessed by the user. For example, a shared structure without a reference count might cause a race condition. Without proper accounting, one process might free the structure whereas another process still wants to use it. Later on, the second process may attempt to use the no longer existent structure through a now invalid pointer. This might result in a null pointer dereference, reading of garbage data, or nothing bad at all, if the data was not yet overwritten. The null pointer dereference causes an oops, whereas the garbage data leads to corruption, and then bad behavior or an oops. I think oops means like the kernel panic, like a blue screen of death kind of thing, but for Linux. The user reports the oops. Let's see here. Yeah. Reports the oops or incorrect behavior. The kernel developer must then work backward from the error and see that the data was accessed after it was freed. There was a race, and the fix is to add proper reference counting on the shared structure. Debugging the kernel might sound difficult, but in reality, the kernel is not unlike any other large software project. The kernel does have unique issues such as timing constraints and race conditions, which are a consequence of allowing multiple threads of execution inside the kernel. Debugging by printing. The kernel print function printk behaves almost identically to the C library printf function. Indeed, throughout this book, we have made use of a few real differences. Yeah, we use printk a lot during our time for the past 17 chapters or so. For most intentions, this is fine. Printk is simply the name of the kernel's formatted print function. It does have some special features, however. Ooh, interesting. Now we're going to learn more about printk. Robustness. One property of printk easily taken for granted is its robustness. The printk function is callable from just about anywhere in the kernel at any time. It can be called from the interrupt or process context. It can be called while any lock is held. It can be called simultaneously on multiple processors, yet it does not require the caller to hold a lock. So it's so flexible and it does so much magic. It is a resilient function. This is important because the usefulness of printk rests on the fact that it is always there and always works. A kink in the armor of printk's robustness does exist. It is unusable before a certain point in the kernel boot process, prior to console initialization. So I'm guessing before we hook up some sort of output, printk is not available. So somewhere in this like where only assembly is probably executing, which is where printk may not be available. Indeed, if the console is not initialized, where is the output supposed to go? This is normally not an issue unless you debug issues early in the boot process. For example, in setup arch, which performs architecture-specific initialization. Such debugging is a challenge to begin with, and the absence of any sort of print method only compounds the problem. There is some hope, but not a lot. Hardcore architecture hackers use the hardware that does work, say a serial port, to communicate with the outside world. This is not fun for most people. The solution is a printk variant that can output to the console early in the boot process. Early printk. Oh, okay, so there is a way using early printk. The behavior is the same as printk, only the name and its capability to work earlier are changed. This is not a portable solution, meaning that it will not work with all architectures with default things, I guess. However, because not all supported architectures have such a method implemented. It might be your best hope, however, if the architecture you use does implement it, most including x86 do, and I'm guessing ARM too. So we're like kind of covered for a lot of cases. Unless you need to write to the console early in the boot process, you can rely on printk to always work. And I think that's true because even when we see the kernel loading during all our times, we would always see some print statements that we made early in that kernel loading process before we even hit the window or the desktop environment. Okay, so log levels. The major difference in usage between printk and printf is the capability of the former to specify a log level. The kernel uses the log level to decide whether to print the message to the console. The kernel displays all messages with a log level below a specified value on the console. You specify a log level like this: printk kern warning, this is a warning; printk kern debug, this is a debug notice; printk I did not specify a log level. Oh, I didn't know we could do it like this. Interesting. Okay. The kern warning and kern debug screens are simple defines found in linux/kernel.h. They expand to a string such as this, 4, or 7. So that's basically the log level, the numeric level. That is concatenated. And I'm guessing the lower the level, the more severe it is. That is concatenated onto the front of the printk message. The kernel then decides which messages to print on the console based on this specified log level and current console log level. Console log level. So that's a variable that holds the current level. Table 18.1 is a full listing of the available log levels. So we have emergency. I guess that's like the worst one. Alert, critical, error, warning, notice, info, debug. Okay. Kind of, if you ever worked in applications before, it's like your regular log levels. If you do not specify a log level, it defaults to default message log level, which is currently kern warning. Because this value might change, you should always specify a log level for your messages. The kernel defines the most important log level, kern emerge, as 0, and it defines kern debug, the least critical log level, as 7. So 7 is the least critical, 0 is the most critical. For example, after the preprocessor is done, the previous examples resemble the following. Print K. Okay, so this is when we substitute these labels into as real strings by the preprocessor. So 4 is going to be the warn, 7's debug, this one's warn. Okay, so the avenue that you take with your printk log levels is up to you. Of course, normal messages that you intend to keep around should have the appropriate log level, but the debugging messages you sprinkle everywhere when trying to get a handle on a problem, admit it, we all do it and it works, can have any log level you want. One option is to leave your default console log level where it is and make all your debugging messages kern crit or so. Conversely, you can make the debugging messages kern debug and change your console level. Basically do anything it takes to get that log level come out. Each has pros and cons. You decide. The log buffer. Kernel messages are stored in a circular buffer of size log buff len. This size is configurable at compile time via the config log buff shift option. The default for a uniprocessor machine is 16 kilobytes. In other words, the kernel can simultaneously store 16 kilobytes of kernel messages. If the message queue is at the maximum and another call to printk is made, the new message overwrites the oldest one. The log buffer is called circular because reading and writing occur in a circular pattern. Using a circular buffer has multiple advantages. Because it is easy to simultaneously write to and read from a circular buffer, even interrupt context can easily use printk. So furthermore, it makes log maintenance easy. If there are too many messages, new messages simply overwrite the older ones. So basically, if you hit the end of the buffer, it just goes and kind of starts logging to the front of the buffer again. It's just circular that way. If there is a problem that results in the generation of many messages, the log simply overwrites itself in lieu of uncontrollably consuming memory. The lone disadvantage of a circular buffer, the possibility of losing messages, is a small price to pay for simplicity and robustness it affords. syslogd and klogd. On a standard Linux system, the user space klogd daemon retrieves the kernel messages from the log buffer and feeds them into the system log file via the syslogd daemon. To read the log, klogd program can either read the proc kmessage file or the syslog, or call the syslog system call. By default, it uses the proc approach. In either case, klogd blocks until there are new kernel messages to read. It then wakes up, reads any new messages, and processes them. By default, it sends the messages to the syslogd daemon. The syslogd daemon appends all the messages it receives to a file, which is by default var log messages. It is configurable via etc syslog.conf. You can have klogd change the console log level when it loads by specifying the -c flag when you start it. Transposing printf and printk. When you first start developing kernel code, you most likely will often transpose printf for printk. I think that means like our mindset kind of just does like a substitution of printf to printk. This transposition is only natural as you cannot deny years of repetition using printf in user space development. With luck, this mistake will not last long because the repeated linker errors will eventually grow rather annoying. Someday you might find yourself accidentally using printk instead of printf. Oh, if that day comes, I will be happy. In your user space code. When that day comes, you can say you are a true kernel hacker. Yes. Okay. Oops. Yeah, okay. I don't know what they mean by oops. I was just guessing it might be a kernel panic. So we'll find out now. So an oops is the usual way of a kernel communicates to the user that something bad happened. Because the kernel is the supervisor of the entire system, it cannot simply fix itself or kill itself as it can when the user space goes awry. Instead, the kernel issues an oops. This involves printing an error message to the console, dumping the contents of the registers, and providing a backtrace. A failure in the kernel is hard to manage, so the kernel must jump through many hoops to issue the oops and clean up itself afterwards. Often after an oops, the kernel is in inconsistent state. For example, the kernel could have been in the middle of processing important data when the oops occurred. It might have held a lock or been in the middle of talking to hardware. The kernel must gracefully back out of its current context to try and resume control of the system. In many cases, this is not possible. If the oops occurred in interrupt context, the kernel cannot continue and it panics. A panic results in an instant halt of the system. If the oops occurred in the idle task, or PID 0, or the init task, PID 1, the result is also a panic because the kernel cannot continue without these important processes. If the oops occurs in any other process, however, the kernel kills the process and tries to continue executing. Okay, so any fatal error. An oops might occur for multiple reasons, including a memory access violation or an illegal instruction. As a kernel developer, you will often deal with and undoubtedly cause oopses. What follows is an oops example from a PowerPC machine in the timer handler of the Tulip network interface card. Okay, so here's the oops. It looks like it has a message here, unable to handle kernel null pointer dereference. So you're trying to dereference a null pointer in kernel space. Virtual address here. Well, that's very early. Okay, and here's a stack trace. Sure. So it comes from Tulip Timer, which was called by the runtimer soft IRQ. So that's the soft IRQ, the bottom half interrupt handler. Okay, so that was a soft IRQ with do soft IRQ off from the timer interrupt, which was the front half of the interrupt handling. Okay. Anyway, PC users might marvel at the number of registers, a whopping 32. And oops on an x86 32-bit, which you might be more familiar with, is a little simpler. The important information, however, is identical for all the architectures. The contents of the registers and backtrace. Okay, so this is the contents of the registers. And here's the stack trace. Okay. So the backtrace shows the exact function call chain leading up to the problem. In this case, you can see exactly what happened. The machine was idle and executing the idle loop, CPU idle, which calls a default idle in a loop. The timer interrupt occurred, which resulted in the processing of timers. A timer handler, the Tulip timer function, was executed, which performed a null pointer dereference. You can even use the offsets, those numbers such as 0x128, 0x1c4, to the right of the functions to find exactly the offending line. The register contents can be equally useful, although less commonly so. With a decoded copy of the function in assembly, the register values help you recreate the exact events leading to the problem. Seeing an unexpected value in a register might shine some light on the root cause of the issue. In this case, you can see which registers held null, a value of all zeros. and discover which variable in the function had the unexpected value. In situations such as this, the problem is often a race. In this case, between the timer and some other part of the network card. Debugging a race condition is always a challenge. So case sim oops. The previous oops is said to be decoded because the memory addresses are translated into the functions they represent. An undecoded version of the previous oops is shown here. So no message, no, well, you have a very vague trace of just the memory addresses. So the addresses in the backtrace need to be converted into symbolic names. This is done via the ksim oops command in conjunction with the system.map generated during kernel compile. If you use modules, you also need some module information. Ksim oops tries to figure out most of this information, so you can usually invoke it via ksim oops saved oops.txt. So it's going to try and kind of parse this information and give back right here, like decode these memory addresses, go back to like the symbol table and like try to fill in with the real function names and the line of code. KL sims. Thankfully, dealing with ksim oops is no longer a requirement. Okay, this is a big deal because although developers might have had little problem using it, and users often mismatch system.map files or fail to decode oopsies altogether. The 2.5 kernel development introduced all KL sims feature, which is enabled via the config KL sims configuration option. This option stores in the kernel the symbolic name of function addresses mapped into the kernel image so that the kernel can print decoded backtraces. Consequently, decoding oopses are no longer requires system.map or ksim oops. On the downside, the size of the kernel increases a bit because the address to symbol mappings must reside permanently mapped into kernel memory. It is worth the memory use, however, during not only development but also deployment. The configuration option config case all sims all additionally stores the symbolic names of all symbols and not only the functions. This is generally needed only by specialized debuggers. The config KLSIMS extra pass option causes the kernel build process to make a second pass over the kernel's object code. It is useful only when debugging KLSIMS itself. Kernel debugging options. Multiple configure options that you can set during compile to aid in debugging and testing kernel code are available. These options are in the kernel hacking menu of the kernel configuration editor. They all depend on the config debug kernel flag. When hacking on the kernel, consider enabling as many of these options as practical. Some of the options are rather useful, enabling slab layer debugging, high memory debugging, I/O mapping debugging, spin lock debugging, and stack overflow checking. One of the most useful settings, however, is sleep inside spin lock checking, which actually does much more. Starting with 2.5, the kernel has an excellent infrastructure for detecting all sorts of atomicity violations. Recall from Chapter 9, an introduction to kernel synchronization, that atomic refers to something's capability to execute without division, the code completes without interruption, or it does not complete at all. Code that holds a spin lock or has a disabled kernel preemption is atomic. Code cannot sleep while atomic. Sleeping while holding a lock is a recipe for deadlock. Thanks to kernel preemption, the kernel has a central atomicity counter. The kernel can be set such that if a task sleeps while atomic or even does something that might sleep, the kernel prints a warning and provides a backtrace. Potential bugs that are detectable include calling schedule while holding a lock, issuing a blocking memory allocation while holding a lock, or sleeping while holding a reference to per CPU data. This debugging infrastructure catches a lot of bugs and is highly recommended. The following option makes the best use of these features. Okay, config preempt, config debug kernel, config KLSIMS, config debug spinlock C. So just enable all of them. Enable all of them. Anyway, asserting bugs and dumping information. A number of kernel routines make it easy to flag bugs, provide assertions, and dump information. Two of the most common are bug and bug on. When called, they cause an oops, which results in a stack trace and an error message dumped to the kernel. So this is forcing oopses. Why these statements cause an oops is architecture dependent. Most architecture define bug and bug on as illegal instructions, which result in the desired oops. You normally use these routines as assertions to flag situations that should not happen. So if bad thing happens, bug. Or even better, bug on bad thing. Most kernel developers believe that bug on is easier to read and more self-documenting compared to bug. Also, bug on wraps its assertion in an unlikely statement. Do note that some developers have discussed the idea of having an option to compile bug on statements away, saving space in embedded kernels. This means that your assertion inside a bug on should not have any side effects. The macro build bug on performs the same purpose but at compile time. If the provided statement evaluates to true at compile time, the compilation aborts with an error. A more critical error is signaled via panic. A call to panic prints an error message and then halts the kernel. Obviously, you want to only use it for the worst of situations. So if some terrible thing happened, issue a kernel panic, right? With this call, called terrible thing is blah. Okay? Sometimes you just want a simple stack trace issued on the console to help you in debugging. In those cases, dump stack is used. It simply dumps the contents of the registers and function backtrace to the console. So it prints the entire stack in the register contents with the dump stack call. Okay. The magic sysrq key. A possible lifesaver is the magic sysrq key, which is enabled via the config magic sysrq configure option. The sysrq system request key is a standard key on most keyboards. Looks like not on mine anymore. I don't have it. On the i386 and PPC is accessible via the outprint screen. I don't even have a print screen either on my split keyboard. When this configuration option is enabled, special combination of keys enable you to communicate with the kernel regardless of what else it is doing. This enables you to perform some useful tasks in the face of a dying system. In addition to the configure option, there is a sysctl to toggle this feature on and off. To turn it on, do echo 1 proc sys kernel sysrq. I think you have to be sudo for this. From the console, you can hit sysrq-h for a list of available options. Sysrq-s syncs dirty buffers to disk. Sysrq-u unmounts all file systems, and sysrq-b reboots the machine. Issuing these three key combinations in a row is a safer way to reboot a dying machine than simply hitting the machine reset switch. If the machine is badly locked, it might not respond to any magic sysrq combinations, or it might fail to complete a given command. With luck, however, these options might save your data or aid in debugging. 18.2 is a listing of the supported sysrq commands. Ooh, there's a lot. So sysrq-b reboots the machine. E sends a sig term to all processes except for init. Okay, wow. To all processes, sig kill. These are very extreme. Sig kill to all processes except init, including init. Dumps memory information in the console. That's useful. Shuts down the machine. Oh, that's a fast way to shut down a machine. But I think these are like really extreme things that you should. Yeah. Okay. All right. The file documentation / sysrq.txt in the kernel source tree has more information. The actual implementation is in drivers char sysrq.c. The magic sysrq key is a vital tool for aiding in debugging or saving a dying system because it provides powerful capabilities to any user on the console. However, you should exercise caution on important machines. For your development machine, however, it is great help. The saga of a kernel debugger. Many kernel developers have long demanded an in-kernel debugger. Unfortunately, Linus does not want a debugger in his tree. He believes that debuggers lead to bad fixes by misinformed developers. No one can argue with his logic. A fix derived from a real understanding of the code is certainly more likely to be correct. Nonetheless, plenty of kernel developers want an official in-kernel debugger. Because it is unlikely to happen anytime soon, a number of patches have arisen that add kernel debugging support to the standard Linux kernel. Despite being external unofficial patches, these tools are quite well featured and powerful. Before you delve into these solutions, however, it is a good idea to look at how much help the standard Linux debugger, GDB, can give you. GDB. You can use a standard GNU debugger to glimpse inside a running kernel. Starting the debugger on the kernel is about the same as debugging a running process. So gdb VM Linux slash proc slash kcore. The VM Linux file is the uncompressed kernel image stored in the root of the build directory, not the compressed Z image or BZ image. The optional proc kcore parameter acts as a core file to let GDB actually peek into the memory of the running kernel. You need to be root to read it, so it's probably like a pathway to the memory addresses that the kernel is working in. You can issue just about any of the GDB commands for reading information. For example, to print the value of a variable, p global variable, to disassemble a function, disassemble function. If you compile the kernel with the -g flag, add the -g to the C flags variable in the kernel makefile, GDB can provide much more information. For example, you can dump the contents of structures and follow pointers. You also get a much larger kernel, so do not routinely compile with debugging information included. Unfortunately, this is about the limit of what GDB can do. It cannot modify kernel data in any way. It is unable to single step through kernel code or set breakpoints. The inability to modify kernel data structures is a large downside, although it is undoubtedly useful for it to disassemble functions on occasion. It would be much more useful if it could modify data too. KGDB. KGDB is a patch that enables GDB to fully debug the kernel remotely over a serial line. So it's through like a serial port. It requires two computers. The first runs a kernel patch with KGDB. Okay, so one computer will run a kernel with KGDB on, and the second computer will debug the first over the serial line. And that's the literally like a serial which is a null modem cable connecting to machines using GDB. With KGDB, the entire feature set of GDB is accessible, reading and writing any variables, settings, breakpoints, setting watch points, single stepping, and so on. Special versions of KGDB even enable function execution. Setting up KGDB and the serial line is a little tricky, but when complete, debugging is simple. The patch installs plenty of documentation in documentation / check it out. Different people maintain that the different people maintain the KGDB patch for various architectures and kernel releases. Okay, getting tired. Searching online is your best bet for finding a patch for a given kernel. Poking and probing the system. As you gain experience in kernel debugging, you gain little tricks to help you poke and probe the kernel for answers. Because kernel debugging can prove rather challenging, every little tip and trick helps. Let's look at a couple. Using UID as a conditional. If the code you are developing is process related, sometimes you can develop alternative implementations without breaking the existing code. This is helpful if you are rewriting an important system call and would like a fully functional system with which to debug it. For example, assume you are rewriting the fork algorithm to take advantage of an exciting new feature. Unless you get everything right on the first try, it would not be easy to debug the system. A non-functioning fork system call is certain to result in a non-functioning system. As always, there is hope. Often, it is safe to keep the remaining algorithm in place and construct your replacement on the side. You can achieve this by using the user ID UID as a conditional with which to decide which algorithm to use. Oh, so based off of the current user, so you can have like a special user that will execute this new algorithm. Okay, that's cool. That's interesting. So it's through the UID. So you can create a different user and then invoke the process as that user, and you can get to use your new fork implementation. All users except UID 777 will use the old algorithm. You can create a special user with UID 7777 for testing the new algorithm. This makes it much easier to test critical process related code. That's true. Using condition variables. If the code in question is not in process context, or if you want a more global method of controlling the feature, you can use a condition variable. This approach is even simpler than using the UID. Simply create a global variable and use it as a conditional check in your code. If the variable is 0, you follow one code path. If it is non-zero, you follow another. The variable can be set via an interface you export or poke from the debugger. Okay. Now, using statistics. Sometimes you want to get a feel for how often a specific event occurs. Sometimes you want to compare multiple events and generate some ratios for comparison. You can do this easily by creating statistics and a mechanism to export their values. For instance, say you want to look at the occurrence of foo and the occurrence of bar. In a file, ideally the one where these events occur, declare two global variables, unsigned long foo stat, unsigned long bar stat. For each occurrence of these events, increment the appropriate variable, then export the data however you feel fit. For example, you can create a file in /proc with the values or write a system call. Alternatively, simply read them via debugger. Note that this approach is not particularly SMP safe. Ideally, you would use atomic operations for trivial one-time debugging statistic. However, you normally do not need such protection. Okay, rate and occurrence limiting your debugging. Often you want to stick some debugging checks with some corresponding print statements in an area to sniff out a problem. In the kernel, however, some functions are called many times per second. Oh yeah, we learned that. If you stick a call to print k in such a function, the system is overwhelmed with debugging output and quickly grows unusable. Two relatively simple tricks exist to prevent this problem. The first is rate limiting, which is useful when you want to watch the progression of an event, but the event occurs rather often. To prevent a deluge of debugging output, you print your debug message or do whatever you are doing only every few seconds. For example, static unsigned long prev jiffy equals jiffies, so that's the rate limiting. And then you have logic to just check to see whether or not it's the appropriate time to print something out. So it's like regular rate limiting debugging user space code. In this example, the debug message is printed at almost every 2 seconds. This prevents any flood of information on the console and the computer remains usable. You might need the rate limiting to be larger or smaller depending on your needs. If you are only using print k, you can use a special function to rate limit your print k calls. If error and print k rate limit, print k kern debug, error equals blah. Okay, fine. The print k rate limit function returns 0 if rate limiting is in effect and non-zero otherwise. By default, the function allows only one message every 5 seconds, but allows an initial burst of up to 10 messages before the cap is enforced. These parameters are tunable via the print k rate limit and print k rate limit burst sysctl respectively. Another sticky situation arises if you try to determine if a code path is exercised in a particular way. Unlike the previous example, you do not want real-time notification. This is an especially sticky situation if it is of the sort where it is triggered only once. It is triggered a lot. If it is the sort of where it's triggered once, it is triggered a lot. Okay? The solution here is to not rate limit the debugging, but occurrence limit it. Oh, okay. So if it appears many times, you wanna just limit up to a certain point of occurrences. Okay, so this one's like 5. Okay, sure. This example caps the debugging output to 5. After 5 such messages, the conditional is always false. In both examples, the variables should be static and local to the function as shown. This enables the variable's values to persist across function calls. Neither of these examples are SMP or preempt safe, although a quick switch to atomic operators make them safe. For temporary debugging checks, you often need not be so fastidious. Okay, here's something I'm very familiar with: binary searching to find the culprit change. It is usually useful to know when a bug was introduced into the kernel source. We call this bisecting too in the industry. If you know that a bug occurred in version 2.633 but not 2.429, you have a clear picture of the changes that occurred to cause the bug. The bug fix is often as simple as reverting or otherwise fixing the bad change. Many times, however, you do not know what kernel version introduced the bug. You know that the bug is in the current kernel, but it seemed to have always been in the current kernel. With a little effort, you can find the offending change. With the change in hand, the bug fix is usually near. To start, you need a reliably reproducible problem, preferably a bug that you can verify immediately after boot. Next, you need a known good kernel. You might already know this. For example, if you know a couple months back the kernel worked, grab a kernel from that period. If you are wrong, try an earlier release. It shouldn't be too hard to find a kernel without the bug. Next, you need a known bad kernel. To make things easier, start with the earliest kernel you know to have the bug. Now you begin a binary search from the known bad kernel down to the known good kernel. Let's look at an example. Assume the latest known good kernel is 2.611 and the earliest known bad is 2.620. Start by picking a kernel in the middle, such as 2.6.15. Test 2.6.15 for the bug. If 2.6.15 works, you know the problem began in a later kernel. So try a kernel between 2.615 and 2.620, say 2.617. On the other hand, if 2.615 does not work, you know the problem is in an earlier kernel, so you try 2.613, rinse and repeat. Eventually, you should narrow the problem down to two subsequently released kernels, one of which has the bug and one which does not. You have a clear picture of the changes that caused the bug. This approach beats looking at every kernel. That is true. Okay, binary searching with Git. The Git source management tool provides a useful mechanism for performing binary searches. If you use Git to control your copy of the Linux source tree, it can automate the binary search process. Moreover, the Git tool performs a binary search at the revision level, actually pinpointing the specific commit that introduced the bug. Unlike many Git-related tasks, binary searching with Git is not hard. To start, you tell Git where you want to begin a binary search. Git bisect start. Then you provide Git with the earliest broken revision. Git bisect bad this revision number. I think that's the hash, the commit. Earliest broken revision, I guess, but that means you already know it, right? If the latest version of the kernel is your known earliest offender, you do not need to provide a revision. Oh, okay. Cool, so it doesn't really matter. Okay, so Git bisect bad is good enough. Okay, you then provide Git with the latest working revision. So the last time you know that was good. Then Git automatically checks out the Linux source tree by checking the provided bad and good revisions. You then compile, run, and test that revision. If it works, you run Git bisect good. Okay. If it does not work, that is the given kernel revision demonstrates a bug, you run Git bisect bad. Okay, so then it uses rinse, wash, and repeat. On each command, Git again bisects the tree on a per revision basis, returning the next bisection as needed. You repeat the process until there are no more bisections possible. Git then prints the offending revision number. This can be a long process, but Git does make it easy. If you think you know the source of the bug, say it is clear in the x86 specific boot code, you can instruct Git to only bisect among commits touching a specified list of directories. Git bisect start -arch x86. This is very useful, actually. You not only for kernel development, but for any real life software repo that is on the Git source control. Okay, so when all else fails, the community. Perhaps you have tried everything that you can think of. You have slaved over the keyboard for countless hours, and indeed perhaps countless days, and the solution still escapes you. If the bug is in the mainstream Linux kernel, you can always elicit the help of the other developers in the kernel community. A brief but complete email sent to the kernel mailing list describing the bug and your findings might help in aid of discovery of a solution. After all, no one likes bugs. Chapter 20, Patches Hacking in the Community, specifically addresses the community in its primary form, the Linux kernel mailing list. Okay. Conclusion. This chapter covered debugging the kernel, the process of determining why implementation diverges from intention. We looked at several techniques from built-in kernel debug infrastructure to debuggers, from logging to binary searching with Git. Because debugging the Linux kernel can be significantly more difficult task than debugging a user space application, the material in this chapter is crucial to anyone intending to write the kernel code. In the next chapter, we cover another general topic, portability in the Linux kernel. Onward. So we're almost done with the book. We only have like 2 more chapters. So the next chapter is portability. And it should be a pretty short one. So thanks.